So I'm going to talk today a little bit about ML and AI models that have the potential to transform health. And we've had some amazing presenters who have been very technical, deep dive, statistical analysis that I couldn't follow because I did really poorly in statistics. And then we had a really great presentation from IBM on clinical care and how a really interesting clinical use case would be designed and presented to as an end user use case, which is great. I'm not going to talk a little about that quite as much. I actually have a very ulterior motive in my presentation today, and that's to convince all of you data scientists to go into healthcare. So I'm gonna pull at your heartstrings a little bit and tell you about why I work in healthcare. So I don't know if you can tell what this is from this picture. This is my niece, Nim. Nim was born in 2010, and she's a healthy little kid. She's in the 95th percentile height and weight. So I'm going to give you the good news at the beginning so you don't think there's a tragic end story here. She's perfect developmentally, but I want to talk about why data science matters in health. I don't know if you can tell, but this is my brother's wedding ring right here. It's about 3/4 of the way up her arm. She weighed 1 pound and 3 ounces, which is just a little bit over half a kilogram. She was 11 inches long, which is about the same length as a Barbie doll. And when she was born, we were fortunate that she was born near an academic research university hospital where there were pediatric specialists who understood her disease, her many, many disease states, and were able to use 6 different information systems that were tied to her body at all times to monitor over 250 data points that allowed her to be developmentally perfect in the end. So this was almost 10 years ago. And none of that technology used machine learning or artificial intelligence or any kind of real rational methodology other than to track data, build specific alerts for different types of illness, and make sure that people intervene in her care at the right moments in time. And consequently, she's an A student. I mentioned she's tall and healthy and perfect. So, and she's my only brother's only daughter, so she's my only niece. So I think it's pretty important that she survived. So this is why healthcare matters. You can talk to financial services people all day long about that extra decimal point that's going to move left or right based on your work. It's all very important, but this is why I work in healthcare and why after a career of chasing whatever interesting problem kind of dropped in front of me, I landed in healthcare and I was humbled by it, and I stayed there for the last almost 15 years. So I want to talk a little bit about women in healthcare. I alluded to this a little bit earlier, is women are pretty amazing. By the way, we listen. So the very first point I want to make is that on average, women physicians will wait almost 3 minutes to interrupt you when you're talking about how you feel. Compared to men, sorry men, I appreciate your allies here, but you interrupt after 47 seconds. And my husband would say that I'm a standard deviation a bit to the left, maybe 2, because I interrupt way sooner than 3 minutes. But on average, we listen, and I think that makes really important differentials in how we deliver healthcare. So when you look at big data, you can see that women actually produce better outcomes than male doctors. Not by a lot, but by 0.5 point. And that matters to the 26,000 people who would otherwise have died last year in the US. And the other thing I would suggest is that women, and especially 40-year-old women, are our target demographic in the healthcare business because they're taking care of their families and their parents and their spouses, and they are making most of the clinical decisions in our world. And even though we're 80% of the people we're making 80% of the buying decisions around how healthcare is delivered at home and in the healthcare systems that we all participate in, we're actually underrepresented as far as decision making is concerned. So it's a traditionally supportive industry for women. So there's 65% of the population that work in health, but not necessarily in leadership positions. And I can speak from personal experience, it's not so much in IT. So I'm really, really, really hopeful that you'll all choose this as a profession. And I can stop right now because I can see smiles and I know you all just were convinced. So, but we'll still talk about AI. So this is my definition and the definition of some of my friends. Artificial intelligence, machine learning, and all these kind of buzzwords and terms are not very well or formally documented. I went to a conference 2 years ago. It was called HIMSS. It's a very, very large healthcare conference in the United States. There were 6 football fields, that's American football, field-sized vendor displays. It's very large. And almost every one of them had a banner that said artificial intelligence. So I went and I talked to a few, and I said, well, what does that mean to you? And they're like, we have structured data. And I was like, and that's AI? And they're like, well, we're AI ready. So AI isn't very well understood, and those defined terms are something that we're working on in the standards world so that we can all kind of use similar terminology. But by and large, what I consider it is basically making machines seem intelligent, like they're acting like we would. And then on the machine learning side, we're actually trying to make machines learn kind of like we would. And then there's this little button called robotics, and I put it in there because inevitably, when I talk about machines that learn, somebody brings up the Terminator and Skynet. And really, robotics is just another vector point in this Venn diagram that suggests that sometimes when we move things around, there's this little tiny segment, her name's Sophia, and she got citizenship here in the Middle East. Right, in Saudi Arabia, which is where I was raised, by the way, in case you were all wondering why I am the way I am. Sophia got citizenship right here in the Middle East. It's quite advanced, it's quite forward-thinking and forward-leaning, and it's amazing. And I mean that with all the love in the world. I am the way I am because I grew up in an amazing part of the world. So all kinds of technologies fit within these Venn diagrams, but my world and what I focus on is really this machine learning bit, and particularly those that look like they might be intelligent. So we will move on to this absolute fact that ML is everywhere. I think some of you might be using Google today. Most of our really cool technologies have embedded machine learning in them. And there's some direct application to healthcare, and I brought this slide up for a reason, is that photos, and we talked a little bit about transfer learning. Is Cassie still here? I don't know if she's here anymore. She's gone, yeah. Cassie talked about the importance of transfer learning and that you need large quantities of data to train really good models. So these technologies, photos and predictive text writing for the inbox application and maps even for recommending pathways that are safe, are things that actually have transfer learning potential for healthcare. So we're going to talk a lot more about like imaging and image detection and the uses of some of these technologies for imaging, and also for some of the predictive text around things like medical records and recommending kind of additional documentation that might be necessary for a medical record. And then for care pathways, it's remarkable how much actual correlation there is to recommending a person with kind of a common healthcare trajectory and traffic patterns. And that some of that transfer learning is actually applicable, that you can make recommendations for how someone's disease might progress, similar to how you might recommend how somebody's traffic experience is going to project. So the fact that we have some of this underlying technology means that we can do a bit more adjustment and training on smaller data sets in healthcare because we have underlying technology that's been trained on very large data sets. And that is, I think, kind of unique. And we make a lot of that available publicly for our startup friends, who's not here anymore. Oh, no. So machine learning isn't magic. We talked a little bit about this word magic. I actually had it in here before. This is not one of the slides I changed 5 times. It's just a new engineering approach. And I want to talk a little bit about why now. Why is it something that we're doing now, right? The idea of artificial intelligence has been around for a very long time, decades and decades. But there are a couple of key components that maybe we didn't have. The first was computational resource. We had some questions about computational resource, and I met a really amazing PhD student who's using some great geo-related, I can't see you. But computational resources have evolved and changed a lot in the last couple of years. And I don't know if you remember, or how many of you might have even been too young to remember, but 8-bit graphics. Do you remember the video games that had the little 8-bit characters and the 8-bit music? Well, over time, we decided that, that 8-bit graphic and music experience was cheesy and we wanted it to improve. And so we invested in hardware that would accelerate and make that experience better. And that's why we have really great graphic cards that are dedicated computational resources to graphics, and the same for music. Well, the same thing is happening for computational things necessary for AI to thrive. And so we have what we call TensorFlow processing units, TPUs or GPUs. And these are chips and capability that's designed specifically to accelerate machine learning tasks. And with the advent of those computational resources, and also the tools that have actually been around for quite some time, and the proliferation of data for training examples, and all of you all who are going to come with really great creativity and ingenuity, it is the time for AI to thrive, and especially in healthcare, in my opinion. So, AI is actually or machine learning is actually super easy. It's the same sort of learning that we do with kids. So let's talk a little bit about how people learn. You start with an input. The machine, which is our brain, makes a prediction about something. How many of you ever tried to teach a child about a giraffe, like what a giraffe looks like? I'm going to say everybody has at some point. When you show them a picture of a giraffe and you say, what is this? And they've never experienced a giraffe before, they're going to say, oh, it looks like a horse with a really long neck. So they're going to make a prediction and say that that picture looks like a horse. And then the truth sayer, the person who actually knows the truth of this, is going to give them some sort of new parameter and say, well, you know, it looks like a horse but has a really long neck. It's actually what we call a giraffe, especially if it has spots of this particular color, or if you find it in a picture book about Africa. And that goes back into the little person's brain. Our little gray matter is really good at adapting to change. And then the next time they see a picture of a giraffe, they're more likely to actually say that's a giraffe instead of a horse, right? The same thing happened when we tried to train Google Images to understand what is a cat with a party hat. And I always use cats with party hats because nobody seems to take offense at that. So first we taught it about cats, and then we taught it about party hats. And a really surprising thing happened. So when you showed them a picture with a cat with a party hat, it was able to predict and label it specifically cats and party hats. And then over time, it got really good at recognizing cats versus dogs, or Persian cats versus Bengal cats, and things like that. So over time, as long as there's a learner or somebody who's going to be the truth teller to give reinforced learning to these algorithms, they're going to get better and better and better. So we thought that there's a couple of things we do well at Google. And one of them is translate, and I meant to do this because I want to talk a little bit about translate. Let's see if it works. No, it's not. Somebody asked about mechanical engineering and whether they should go into mechanical engineering. She's over here. She's gone? Okay. So my undergraduate degree was in political science and Middle East area studies with an emphasis on Arabic and Turkish. Not very conducive to data science, but that just goes to prove that you can apply data science to just about anything. So the Translate product, which can run offline, used to be about 500,000 lines of code, which was really long, and it wasn't that great. I don't know if you all use it very often now, but it got a lot better very recently. And the reason it got really a lot better is that it started using deep neural networks and the ability to use machine learning and reinforced learning to improve its capability. But it also had a really remarkable effect on the size of the code. It went from 500,000 lines of code to 500, which meant you could download it and you could work with it offline. It didn't need the cloud anymore in order for it to work. And that's also a goal for us for some of these medical applications, is that most of the world doesn't have ready access to the internet, but does have a significant need for healthcare. So we're focused on a couple of things that we think will make a difference in the world. And the first is around diagnostics. And I'm going to spend most of my time on diagnostics because I have a short period of time to be successfully on time today. So we thought, and we talked a little bit about inspiration, we thought, you know, diagnostic accuracy is not so great. So if 1 in 12 people diagnosed with breast cancer, most of whom are women, get a bad diagnosis, that means that they're either living with a diagnosis of cancer when they are actually not ill, or they were misdiagnosed and not getting treatment. That's a pretty terrible statistic. So we thought, you know, there has to be an opportunity using machine learning to do better at this particular thing of diagnostic accuracy. So we took a look at 2 different types of modalities, and we took a look at what kind of data could we get, and how definitively could we train a data set. And this goes to some of the conversation we had earlier about choosing the right sorts of problems to solve, and knowing that you're going to be able to improve on that model over time. So we took a look at things like cancer pathology and diabetic retinopathy. So for those that aren't familiar, if you have diabetes, there's an effect on your eyesight for a certain population that can actually lead itself to blindness if not treated. And the treatment isn't terribly invasive or difficult, but you have to be screened routinely, and you have to get treatment pretty quickly once you're diagnosed with the potential. But unfortunately, there's a real lack of ophthalmologists in this world, and particularly in the third world. So screening is actually not as available as you would think. So then we took a look at, and it's very clear, when you take a look at the picture of the eyeball is called a fundus image. If you take a look at that image, it's pretty clear. You either are or are not something, right? So you have a fairly definitive diagnosis. And if you take a look at a cancer patient or a pathology slide, cancer may not present for some number of years. So it's not super clear that when you're training a model that it is or isn't cancer, because diagnosis comes sometimes very much later than the actual pathology slide was taken. So we took a look at diabetic retinopathy and thought, let's train on something that we can actually prove is effective. And we looked at diabetic retinopathy and its pervasiveness in the world and said, well, there's about 415 million people with diabetes. And all these folks are at risk for going blind. That seems like a really big problem. And we like to solve really big problems. So we started by saying, well, we don't have a lot of data. Where can we get data? But what was also interesting, and I want to make mention of this before I move to the next slide, is that the underlying ML modeling was the same as for the cats with party hats, right? We were just training it on fundus images using the same neural network that I showed you a moment ago. Oops, did I? Maybe it's ahead. I moved them all around while I was doing my thing. It's using the exact same neural network model as a normal image would use for Google Images. It's just that we trained it with fundus data instead of with cats with party hats. So that meant that we needed a lot less data in order for us to take the existing model that we transferred into this space and then retrained on this particular illness. So we went to India, particularly, and it wasn't for the reasons some people would try to project on us. It wasn't easy. No clinical research is easy. But we went there because there was a real need. And our CEO is from India. And we wanted to make sure we were making a difference for a population that didn't necessarily have access to first world health. Hi. ACEs. So we thought, well, let's go here. And we're in a country where about 45% of people who have this illness might go blind before they can even see a screener. And that's a really terrible outcome when it's completely preventable. So we collected a bunch of pictures of eyeballs, and then we had to label them. So this is really hard in healthcare. We talked about labeling data, and we talked about needing millions of records for some types of learning models. And one of the reasons transfer learning was so important in this space is that it would be incredibly costly, if not impossible, to get 1 million of these things graded and labeled by a trained clinician, right? So, did I mention how much I love photo evidence? So we had a large quantity of records, in this case about 9,000. We hired the best ophthalmologist we could find to do a really great grading effort, and we graded on a 5-point scale between no diabetic retinopathy through proliferative diabetic retinopathy. It was really amazing that doctors don't even agree with themselves. So if I can give you one piece of advice at the end of this presentation, always get a second opinion, because they really, 60% of the time, they don't agree with themselves. So we had to get a committee, actually. We got several ophthalmologists to look at each one of these images and so that we could make sure that we didn't introduce inappropriate bias to the data. And we applied, here's my slide. We applied the same neural network related methodology as we did for cats with party hats on the image search, and just trained it with the fundus image and these very highly accurately graded retina images. And then we added a little bit of extra information just to help with us, what we thought the image quality was, because they come from different types of cameras, and whether it was a left or right eye, and what kind of field of view was the camera representative of. And we came out with some pretty amazing data. So based on, we built a model. We felt it was pretty accurate based on independent validation data. We found that we were actually really, really good at the same level of sensitivity that was expected for diagnostic care, but we were much more specific. We were much more accurate. So we didn't get it wrong, but we also got it right, which is better than just getting it right. And what we also found was that we were on par with, if not slightly better than, ophthalmologists that we had hired. Now, the one statistic that's not on here that I want to really emphasize is that when you combined the algorithm and the ophthalmologist, the number was 98%. So this is why when people are concerned that we're going to replace doctors with technology, it's not about replacement. It's about taking away the redundant tasks that make doctors tired, unhappy, miserable even, augmenting them with tools and capability that allow them to focus on exactly the right things, and it actually makes both parties better. So pathology is super hard. So we took that learning, and we said, let's go look at pathology, and you saw a much better presentation than this on pathology just a moment ago. But I want to give you a kind of an understanding of just how huge these images are that are taken for cancer patients. Like when you take a picture of a path slide, the quality of that image is incredible. It's 150,000 by 90,000 pixels, and a tumor could literally be a couple of pixels across. So when physicians have to look at a path slide and try to find out whether somebody has a cancer, it is incredibly arduous work, and it's really easy to miss, especially small issues. So the system is incredibly good at really monotonous, boring work that our gray matter brains don't like to perform. And so this is an ideal task for a machine learning algorithm. The challenge is really about data. And I know we've all talked about data a number of times, but I want to talk about the healthcare-specific rationale for why health data in particular is really hard. So data inconsistency in healthcare is a fact of life. I think that anybody how many of you have ever worked with health data? A good number of you. How much of it was like actually useful? Shui shui? See, my undergraduate degree is really helping me out here today. My experience with healthcare data is that in the United States especially, where electronic health record adoption was really kind of advanced, we incentivized through federal grants and the role of government in some of these programs, it was over here earlier, was to incentivize the adoption of technology and the creation of data. We incentivized the adoption before we created standards for what those systems should look like. And we're going to get a really awesome presentation by Epic because I think that you can make this case better than anybody that there were attempts. We tried really hard to make the data standardized, but in fact, most people kind of adopted the technology in whatever way was least disruptive to their local implementations. And so they used different data labels for different things. You know, some people said gender, some people said sex, some people used FM, some people used 01. Just the way that it was adopted was just different. And that means that when you collect data from multiple sources, they don't match up. You have to do a lot of data cleaning. And identity is really hard to prove in healthcare as well. At least in the United States, we don't have a national ID number. Do you have a national ID number in Lebanon? No. You probably have a similar problem to us then, which is that data matching is really hard. We get a lot of duplicate data. We get duplicate medical records even within the same medical system. And so it's really difficult for us to get complete data. It's really difficult for us to get clean data. And it's really, really hard to clean it from and remove all the identifiers necessary for clinical research to be really effective and easy. And when you need a lot of data, getting it labeled in such a way that it can be used for machine learning tasks is really expensive because you need clinicians to do it for the most part. Or you need to outsource it to third-party countries, and a lot of people do not want their health data to be leaving their jurisdiction, their local countries. So it's really, really hard to get it clean, to get it consistent, to get it labeled, and only then can you build a machine learning task. And I was joking with one of my team members the other day that we spend 80% of our time on acquiring data and only 20% modeling. And he says, Jutta, he says, you spent 14 months getting me the data. It took me 2 days to build the model. That's no joke. The modeling tasks are not that hard, but getting the data clean, ready, and capable of being used is actually that challenging. De-identification and anonymization is almost impossible in this day and age, and not just for Google because we have a lot of data. It's just that people have become so unique, and the largest number of public data sets ever in our existence are now available for comparison. To prove de-identification and anonymization is really almost a nearly impossible task under especially the GDPR rules. And so it really impacts medical research in a pretty substantial way. We were working with one country on a research project, and that country actually decided to shut down all medical research, not just our project, but all medical research until GDPR shook out. So this is the new privacy law in Europe. It makes it really difficult to understand how anonymization and pseudo-anonymization applies to health data. And so since the national health system we were working with was also subject to citizen concerns over how their data is used, they chose to just stop medical research completely until this law played out in courts for a while. And how tragic is that? As data scientists, you should be as appalled as I am. So, since I'm nearly out of time, I did want to talk a little bit about why healthcare is the place to be, because I'm still selling, I know. So healthcare investments have been top of all industry lists in AI since 2013 when this particular study began. And over the last year and a half, 2 years, investment dollars have become even more significant in the spaces of healthcare AI, computer vision, business intelligence, and smart robotics. So these are the kind of the big prime areas where AI investments are occurring. This is where a lot of startups are getting funded. This is where a lot of businesses are hiring. So I would still suggest that healthcare is top of mind for most people. I think that you see it in the news pretty much every day. Oh, I've been seeing Google's AI projects on the news a lot lately too, where we're trying really hard to advance healthcare in AI and making some substantial investments in that space. But it's also important for you to note that the AI global talent pool is really small, that you guys are special. Choosing this as a space is I think, career advantageous. That according to this report from the Gagné report, there's only 2,200 PhD-educated data scientists in this field in the whole world, and that only 3,000 of them are looking for work. So I know that in the Silicon Valley area, you can't hire a data scientist with any kind of AI experience right now. There's just nobody on the market. So this is a great place to spend your time. This slide would recommend healthcare, just like my pitch at the very beginning. But I would suggest that your interest in the space, your interest in being a data scientist is substantial, and please do choose healthcare if you decide to go to market with your skills outside of academia. Okay, thanks.